it's my pleasure to introduce Barbara Belvisi. Barbara is an extremely talented entrepreneur, and like Elon Musk, is a person that could make a great deal of money in almost any line of business, but she's chosen to make her business making humanity multi-planetary. In her case, solving the problem of sustainable life support. It's necessary for human development to space and has many applications on Earth, as I'm sure she'll make clear. So without further ado, Barbara Belvisi.
Hi everybody. Hello, Robert. I'm very happy to be here. Awesome conference. We met a year ago. Was my first time attending the Mars Society conference. I'm very honored today to be with you and to present to you all a bit more about the work that we're doing and the mission. Yeah, let's go. So I'm gonna share some presentation here. Okay. So I'm the founder, CEO, and product lead at a company called Interstellar Lab. So we're a young startup, started the company actually 2 years ago, September 2018. Did a year of R&D, spending most of my time with people at NASA, and I was lucky to spend actually a month with Robert in Colorado. And we started operation only a year ago. So the problems we're trying to solve, so basically we're making the parallel between the two planets, the Earth and Mars. So on one side, you have the Earth, and that is going right now, under, dramatic events, and the problems we're facing right now, not only regarding, climate change and the loss of biodiversity, but what we believe is that it requires a new approach to implement regenerative environmental solution on this planet. And for us, it's a necessity that we make this change, so that we implement integrated solution when it comes to food production, water treatment, and waste management. And this has to happen now. And if you look at Mars, it's pretty interesting because it's kind of a mirror for what's going on Earth right now. And if you think about, humans going to Mars and bringing life to this planet, to go there, sure, we need a rocket, but also we need the life support system. We need the life support system to support human life. And if you think at what it means to have life support system on Mars, it also means an integrated solution, a closed loop system where basically you can, provide the food, you can recycle the air, recycle the water, and treat the waste. So in a very interesting way, the solution we need in the future to live on Mars are very similar that we need to implement on Earth. So those are the two problems we're trying to tackle. And in terms of timeline, you have Earth right now, and Mars going to happen in 4 years from now. Eventually we'll send the first Starship will go there. Maybe 15 years from now, we'll be able to send first human mission there. So it gives us a little bit of time to test the system before we go to Mars, but at the same time, we need to implement solution now on Earth. So the product we've been developing, it's called eBIOS. So it stands for Experimental Bioregenerative Station. So it's a station. I often say that we're doing space station on Earth. It's a completely closed environment, sealed. It's designed as a closed ecological system, and it's designed to fulfill all the nutritional, the physiological and psychological need for human to live. So each station, oops. Here we go. Each station is designed as a combination of modules. This is what you can see right now. And so by combining different modules, basically we can build a village, and we can grow and support life of more and more people. So a module, we call them flowers because they look like flowers, and we love nature, we love the earth, so we take a lot of inspiration from nature. So each module is composed of 4 units. One is the habitat section, and the 3 other domes. So 2 are dedicated to food production. And another one is dedicated for a centralized water and waste management system. So we do everything internally. So we have architects, engineers. We do our own design. We develop our own, structure, deployability, material system, yeah. So that's how it looks like. You can see here on the back the size of a human, so which gives you a little bit of a perspective on how big is the station. But basically, it's around 750 square meter ground surface, a little bit more. We're still working on the sizing, but that gives you a rough idea. So I'm French, so I'm speaking a square meter and not square feet. So a little bit more about each dome. So each dome is, so as I said, completely sealed with its own environmental control system. And so it means that we're going to have different atmospheric conditions inside each dome, different temperature, different humidity, different different atmospheric. Sometimes we'll boost the CO2, and especially when it's for food for production, and some other times, it will be more. It will fit more human needs, and especially when it comes to the habitat. So this dome is the aeroponics dome. That's not the latest design. This one is not optimized for the surface. But so the aeroponics dome is very dedicated to food production, but very food production. So what is very hard when you build the closed system is actually to close the food loop. And so to close the food loop, we have an approach combining aeroponics and greenhouse. And so on the aeroponics, we've been designing our own A-frame system to be able to grow a lot of different crops and a lot of different species. And this one will be really, so it's like high intensive agriculture. And at the same time, not using, so aeroponics allow us not to use a lot of water, to recycle the water. And we use LED to boost the light inside the dome. The dome is completely opaque, and that's a big difference between the aeroponics dome and the greenhouse dome. And so it's really, and there we're going to boost a lot the level of CO2, and we're going to play a bit with temperature so we can fit exactly what the different plants need. The hard part about what we're doing is that we have a high crop diversity, because we're trying to fulfill all the nutritional needs, and at the same time break diversity, because if you keep eating sweet potatoes all the time, you're going to be pretty depressed. So you need a lot of different food, so won't be eating the same thing. So that's one of the reasons why we have a high diversity, but there is also something else, and I will tell you a bit more after. The second dome is it's the greenhouse dome. So it's a subtropical greenhouse. This one is less about intensive agriculture. So it's more about growing fruits, so trees, because you can't grow trees in an aeroponic system. So it's fruit subtropical trees. Mostly it's going to be dwarf trees with the specific. So it's going to be soil, but we're going to test different things, especially different substrates. And to see how the plants are reacting. But it's also a place where we're not targeting here like very high efficiency food production system on the greenhouse. What we're targeting also is to fulfill the psychological need of humans. So I mean, we've seen, and especially during this pandemic, that human, sure, we need contact with other human, otherwise we feel pretty depressed. But we also need contact with nature. When a human being is for too much of a time separated from nature, we don't end up well. so it's part of also the vision of becoming a multiplanetary species. I mean, it's not going to happen right now, but in the coming years. But bringing plants and bringing life to another planet, it's also it's for me, for us, it's like a mandatory to the well state of human, their psychological stability. The last dome is the water and waste treatment system. So each dome actually, so as I said, it's a closed system, so they will have their own atmospheric condition, but also at the dome level, we will try to recycle the water as much as possible. And so there will be some water loop inside each dome, but then there will be also a centralized system that will be more dedicated to treat actually the human waste, so the black water, and all the organic waste. So the treatment organic waste that are coming from the greenhouse and the greenhouse and the aeroponic domes. It's going to be treated in the other dome. Probably for the first one, what we have different possibilities and different solutions, but what we've been looking at is a, you know, kind of standard and easy way to turn organic waste into nutrients by using aerobic and anaerobic system. And for the treatment of black water, a combination of different systems, you know, UV treatment, reverse osmosis, probably some, you know, biological approach. One thing that for us is important, even though, you know, it's called bioregenerative, to reach an entirely system that is bioregenerative, needs a little bit of time and testing. So we are combining both bioregenerative and physico-chemical solution. And we're gonna iterate and implement different system and solution until we figured out what's the best system. And there might be several, actually. It might be not only one solution, there might be different combination, depending also on the different crops that are selected for the station. So to design such station, you actually need a lot of preparation before jumping into the hardware. So it means that you need to estimate the different flows. I'm just going to pause here a bit. Need to estimate the different flows. So what we did at first, we started with a mass balance model with a set of stoichiometric equation to trying to understand the difference, how the different molecular reaction will happen inside the station, and then estimate the different flows. And so the variation of CO2, the variation of O2 over time, how much water is needed, how we can plug the different water system. But at the very, very beginning of that is the crop selection. So depending on which crop you select and what is their production yield, from the yield prediction model, then it has a lot of influence in terms of the variation of O2 and CO2 inside the station. So to do that, we build a simulator. And so the simulator is working, so it's working like this. This is what you can see right now on the screen. But basically, so you start a simulation. The first step to start a eBio simulation is to enter the requirements. Requirements is it's basically the number of participants. Then if you want to balance if you want to optimize the system for having like less surface area or like a better water optimization system. How much crop diversity are you targeting? And then the different technology that you want, aeroponics, subtropical greenhouse, we're gonna add much more of a time. And most importantly, it's all about covering the nutritional needs. So do we want a full coverage? Do we want to, is it like a purely vegan diet that needs to fulfill all the needs? Or is it just, some add-on to another type of diet? So I'm just gonna apply. Voila, and then you run the simulation. So we build a algorithm that is basically tapping into a very large database of different crops that we build using the FAO database, and then mixing with different data, looking a lot at what the NASA Kennedy Space Center, all the plant team has been working. And so we developed our own algorithm. So it selects the crops, and then it tries to implement into the aeroponic system and the greenhouse system. So you can see, like this is an example of one simulation. So it's coming up with like 35 crops, and then it's given like all the nutritional values basically that you will get based on this selection. So you can run different selection. I'm just gonna move forward a little bit faster, and then you can compare the different selection. So when you set and you compare the different selection, then you can run the simulation for the station. So the algorithm will then calculate and estimate all the flows and all the variation and predict basically what's going to happen inside the station. So what you get at the end, when the simulation is ready, is basically dashboard and prediction of the CO2 level, the O2 level in the different dopes and the different section. You can also follow the different tanks level based on the optimization, and then see when it's going to be the CO2 scrubber activated, and what are the level the level of the different gases inside all the station. Then the goal is basically to connect this prediction model into the station. So once the station is built, our vision is that it needs to be it needs to be monitored, and you don't want too much human intervention. Like you don't want to end up with a mission control that is so big and requires so many people to manage a station. You want the station to be self-sustaining and autonomous. So for that, you need the prediction model, and then you need to put the sensor inside the station, get the data, and then mix the data with the prediction model. And so you adjust basically the prediction model based on real-time data that you're getting. So it means that the station requires a lot of sensor inside. And then after you run the simulation, and that's a dashboard. We don't have a station running yet, so that's a visualization of the dashboard. But this one is not running with an actual station. But then you'll get basically your module, and same, you can follow what's going on inside the greenhouse, inside the different domes, the temperature, the humidity level, the atmospheric condition. The heating and cooling system, which is super important. And also when it comes to the waste management system, basically how, is going the aerobic composting and the anaerobic digester. So for us, the software part in what we're doing is very important, because it will, it can be a base also to, when you develop a station, then you can plug in different systems, but you need a cooperating software. And so that's what we've been focusing on actually the first months of operation of the company. So what it means to live in eBIOS in the station. So why, the plan is to build a 10th station on Earth. Then to iterate on the system and on the technology to make the technology more affordable, and at the same time to test how we can combine different things and different hardware all together, so we can build a sustainable life support system that eventually will be able to put on the moon, and then to put on Mars. I think moon is awesome. It's going to be a very important stepping stone to test different systems before we go to Mars. But Mars is very different, and especially when it comes to life support systems. With the moon, you can keep on having an open supply approach, because it's so close to the Earth that you can still ship water, ship foods, like get the waste back. When it comes to Mars, it's pretty far away. So you want to have something that is working by itself. And so back to living inside the station. The station will be dedicated, of course, for half of the year will be dedicated to scientists and astronaut training. Scientists to run experiments with us, and to access the data, access our software, and help us optimize and optimize the system. It will be open for astronaut training to test what it means to live in a completely closed environment, and to prepare for a man-made mission on future planets. But the other half of the year, and that's something that is very important for us, it will be open to family and the general public, because we want those places to be very educational, inspiring, and you can tell if you look at the project. It's of course, there is a lot of inspiration coming from Biosphere 2 that we really adore. What those guys did in the 90s. I mean, it was very, very visionary. I think it's great there was this experiment, because it's allowing us to leverage on what went wrong there, and try not to do not mistake, but to leverage on what they learned. But it's also, this project there is also a lot of inspiration from the vision of Walt Disney, and especially Epcot. So the experimental prototype for the community of tomorrow, which is now an entertainment park in Florida. But the vision of Disney was really to create a place where people will go, and this ever experimental city, they will learn new ways of living. And so that's also a reason why our station will be open to the general public, because we want people to go there to experience, okay, maybe a little bit like the Martian on Earth, but also to learn how to live in a regenerative way. Because when you're in a super small closed loop system, you understand much faster the impact of your action in the environment. And that's one of the problems that we have right now on Earth, is that it's hard for humans to see the consequences of the action we're having. So it takes a little bit of time. And versus in a closed system, the reaction are much more faster. So we believe those places can be a very good way to help humans understand the consequences of their action and how they can live more in harmony with nature. So what's the plan? So we want to build, as I said, 10 stations over the 10 coming years. It's an ambitious plan. We're gonna go step by step. I mean, very aware of the challenge. yeah, we're very aware of like the difficulties and all the work that needs to be done. I think is also that we don't know what we don't know, so we need to move forward and build stuff and iterate to learn more and to develop the system. But that's the plan. So which year? 2020. So next year we're targeting on having 2 modules operational. So one module is designed for 5 people, support lab of 5 people. One's going to be in Paris. The other one is going to be in California. A little bit of a reference also to Disneyland and being there. We're not an entertainment park, but whatever. Then we're targeting to go to Florida. I hope we'll be able to open something at the Kennedy Space Center, or at least next to them, and eventually iterate more on collaboration with the plant team there and the work they've been doing over the past year, which is really truly amazing. We're also very close to Saudi Arabia. There is a beautiful desert called Alula, archaeological site, and that has some important things that were discovered there about space exploration and the stars. And we're also targeting in 2023 Japan. I mean, this is an amazing place. We can't wait to be there. We will need some iteration in our design and our system because right now we haven't taken all the. It's going to be. We need a bit of iteration, especially on the structure, to make sure it will fit the different environmental condition, and especially the one that you can have in Japan. But that's the 5 first location. We need 5 more on Earth, but we have plenty of time to decide where to do it. But probably we're going to put one also in a very in a very cold area, and I hope also one in Africa. Okay, and that's a render of how a station will look like on Earth. And this one is a bit different from the previous module that I showed you. This one here, you have another dome, which is dedicated to a biological water treatment system. So that's a concept that we started developing 8 months ago, which is a constructed wetland. But it's the technology readiness level is like really too low right now to put that into our 2 coming modules that are coming next year, but this is something we're going to put probably in a module in 2022. We still need to do a lot of testing there, but it's a very good way to get actually potable water from black water directly. So it's super interesting how biology can help us. Okay. So I take the opportunity of doing this opening keynote at the Mars Society conference to it's not an unveil, but it's to introduce you to our first product. So over the past few weeks, we've been super busy with the team. I mean, we're busy, but it's been a bit crazy, and so we've been working on the prototype of our food production system. And we call this prototype Baby Dome. So that's Baby Dome here that you can see inside a building. So we're not saying where, because we're going to announce that at the end of November. But it's some place in Paris where there is a lot of startup and innovation. So we're preparing to put it there eventually before the end of the year. I mean, that's the target. That for Christmas there will be an operating Baby Dome somewhere in Paris. So Baby Dome, so it's a sealed biodome. So it's basically a prototype for our food production system. It's designed as a combination of a subtropical greenhouse and an aeroponic system. So it's completely sealed, and you can see there is an airlock here. I'll tell you a little bit more about the structure. It has its own closed-loop water treatment system, which is very simple on this one because we don't have black water, because we don't have humans living inside the dome. It's like purely for food production. So that makes it a little bit easier. Plus, we have we close the loop of water by catching basically water that is in the air. So that allows us to really like reduce the consumption of water compared to traditional greenhouses that you can find on Earth. It's a completely controlled atmospheric and air system. So basically the way it works is that, so Baby Dome is breathing, so when you take a breath, it inhales atmospheric gases, so ambient air. Then the ambient air gets inside, and then we play a little bit with the level of CO2. So the target was not to put CO2 tanks because, we have CO2 in the atmosphere. And also, if you put a greenhouse on Mars, I don't see the point of bringing CO2 tanks when it's, in situ, you have a lot of CO2 around you. So it needs to be a system that doesn't need tanks to put CO2 inside, but want to scrub CO2 basically by the ambient air that is around the dome. And inside, of course, you have, as always, a set of sensors to be able to track in real time the data and then to adjust with the prediction model. Exactly kind of like a simplified version of the prediction model that we build for an entire station. This one is much more simplified also because we don't have human in this loop. At the baby dome level, we're not dealing here with the organic waste. So the organic waste will be taken out of the dome. But baby dome works as a, it grabs CO2, it grabs atmosphere, it grows the plant, you recycle the water inside, and then it produces the food. And what
Hello,
I think
Barbara, 5 minutes, please, and then we have several questions.
Okay, cool. So what I think, I think this product is awesome because as I said, it's a prototype for like our food production system, but it's also showing how space technology can provide solution for Earth right now. So Baby Dome is providing food for 3 people. And if you think about how much land you need on Earth to provide food for 3 people, it's like 3,000, like it's almost 4,000 square meters that you need, and Baby Dome is less than 30 square meters. It reduces the water need. Like you need much less water to produce the food inside Baby Dome than to produce in traditional agriculture. Plus it captures CO2. Like there is no leakage of CO2 because the membrane is like completely isolated. So it takes the CO2 and it just releases O2, which is really cool. And it fosters biodiversity because we have this constraint of providing, all the nutritional food that people need. So we're saving one of the biggest challenges that we have on Earth. That's our aeroponic A-frame. Right now, we're selecting our partners for the LEDs. That's some of the dwarf trees for fruits that you will find inside Baby Dome. A little bit more about the structure. I'll pass very quickly, but you have a sealed base where you'll find all the heating, water, and HVAC system. And on top, you have an inflatable membrane, which is made of ETFE and aerogel, which is patented, that we patented and developed ourselves. That is very easy to deploy and can be very helpful if we go to Mars. So here you see aeroponic greenhouse, the base, which will be most probably done of a composite material. We still figuring this out. And at the top, the membrane, the inflatable membrane, which completely sealed the dome. So that's Baby Dome on Earth. And that's what we're planning on doing, okay? Paris, then Saudi Arabia, then in Los Angeles, having 2 baby domes there, and then starting building the first module in Paris and then the first module in California. But also our goal is to put Baby Dome on Mars. So that might not happen, right now. There is a lot of iteration we need to do on the product. It's not going to be the same membrane. It's not going to be the same deployability system. But one of our goals is to, protect life on Earth and bring life to other planets. And I find it like, super exciting, like waking up every morning, be like, okay, we are developing and designing a product that is like solving so much problem that we have on Earth right now. But at the same time, we're working for the multiplanetary plan and putting a greenhouse on Mars and showing to people that we'll be able to bring life to another planet. I think that's awesome. And I think it's giving a very optimistic view of the future that we can bring to humanity. Okay, that's us, the team, our small team, 15 people. There is one person that is missing in this picture, but we're gonna take another picture with him on it. Super extraordinary people, very motivated, very passionate, talented, multidisciplinary team from NASA, SpaceX, from Wageningen University, Walt Disney, Airbus, Safran. I mean, super, super cool. I love you guys, and I'm super glad you're in this journey with me. Yeah, the team's growing. We're hiring more people at the end of this year in California and early next year in France. So if you want to join us to build a future full of life on Earth, on Mars, and beyond, please feel free to reach out.
Thank you, Barbara. We have several questions and about 1 minute to answer them.
Sorry about that.
Wonderful presentation. How many people can the flower accommodate?
5.
5 people. Now, will there be sections for individuals or will it all be group living?
No, section for individuals inside the habitat.
Okay, wonderful, thank you. And are these, this is from Stephen, are these for use on Mars only, or can they be used on the moon as well?
So right now it's designed for Earth. We need iteration on the material and the membrane system, so it can be used on Mars, because obviously we don't need to be protected on Earth from solar radiation, so which our material it's not doing right now. So it will need an iteration for Mars. We'd love to deploy one system on the moon. The thing is that on the moon, you don't have season, and so for the greenhouse it might be a little bit more complicated with more LEDs, so more power required, but definitely we want to try to put one of these systems on the moon.
Okay, and our last question is from Dr. Zubrin. He would like to know how you feel about putting a baby dome at MDRS.
I'd love to do that, Robert. I'd love to put baby dome at MDRS. I'm a huge fan of what you've been doing there with the analog. So yes, all in.